In previous videos, we have talked about applications of VBT to octahedral complexes. That was inner orbital and outer orbital complexes. Now we are going to talk about tetrahedral complexes. Tetrahedral complexes contain sp3 hybridization. Both s and p orbitals belong to same shell Ns and Np. Example, nickel chloride, tetrachloride. Now we will explain it in this structure. Here it is explained here. Here you can see structure of NiCl4 2 negative is explained. Applications to tetrahedral complexes. NiCO4 shows tetrahedral geometry, justify it. Nickel is in zero oxidation state. CO is strong field ligand and cause pairing of electrons from 4s to 3d. The vacant 4s and 4p orbitals mix to form sp3 hybrid orbitals. This is diamagnetic because the valence electrons are impaired, so it shows a diamagnetic behavior. Because it is strong field ligand, so electrons will be paired up. The group 2b metals like zinc, cadmium, mercury in their +2 oxidation states are commonly involved in tetrahedral complexes since they all have D10 configuration. Hence, their inner d orbitals cannot participate in hybridization. Zn(Ni3,4) blue positive is a tetrahedral complex. Here you can see ammonia is the strong field ligand. So it also shows the diamagnetic behavior. Applications to copper +1 is also D10 ion. This also represents the electronic configuration of diamagnetic tetrahedral in copper cyanide. Cyanide is also a strong field ligand, so it also forms the diamagnetic complexes. Most of 4 coordinated transition metal complexes are square planar and dsp2 hybridized, utilizing dx square minus y square orbital and central metal ion. Metal ion exhibiting D10 electronic configuration display dsp2 hybridization. The 8d orbitals can be punched up into 4 or 5d orbitals. Here you can see which orbitals are empty, which mixes with empty 1s and 2p orbitals to form dsp2 hybridized orbitals, and this will form the geometry of square planar geometry. Okay, these dsp2 orbitals are then become available for occupancy by 4 electron pairs from ligands. Here you can see in the structure, this is square planar and diamagnetic complex. VBT, what VBT predicts? Paramagnetic 4 coordinated nickel 2 ion complexes are tetrahedral, while diamagnetic 4 coordinated nickel complexes are square planar. What is the reason behind it? Reason is ligand. Here we have Cl, which is a weak field ligand. Here we have Cn, which is a strong field ligand. Now we move toward the exception. Ni3, it is a strong field ligand. So it should have a square planar tetrahedral geometry, but it exhibits square planar geometry, dsp2 hybridization, which was determined by X-rays. Here you can see in structure. Since 4pz electron is in higher energy state, so accepted lost easily, and Cu Ni3,4 positive 2 could be oxidized to Cu Ni3,4 plus 3. The oxidation is not observed for Cu Ni3,4, so it is exception. Huygens considers that the outer d orbital is involved in sp2d hybridization. What are advantages of VBT? Explain the structure and geometry of complexes, successfully explain the paramagnetic and diamagnetic properties of complexes, explain the arrangement of electrons in metal d orbitals after complex formation. Limitations. does not explain color and many chemical properties of complexes, unable to explain magnetic moment data for some complexes, cannot formulate a VB picture of four coordinator complexes without knowing its geometry, do not explain non-involvement of third p orbitals in case of dsp2, as we seen in the last example, does not explain bonding of Cu2 positive complexes, CuNi342 positive, does not account for relative reaction rates of analogous metal complexes. Too much stress is laid on metal atom, ignoring the importance of ligands. That's all.